Good evening, and welcome to the Secure UI Reading Group, Episode 1, where we will be reading User Interaction Design for Secure Systems by Ka-Ping Yi. If you're anything like me, you build computer systems where security cannot be a second-class citizen in your design considerations. And so in this reading group, we're going to read a series of papers written by a lot of very thoughtful people from the history of computer sciences, um, where they're thinking about computer security from a user's perspective. And we're going to think about what kinds of user interface patterns make computer systems and different software secure and securely usable. Because you can talk all day about making a computer secure, but if a user doesn't know how to make it secure for themselves and use it coherently securely, then it's not really secure, is it? The system has a person as part of it. And so we're going to really be taking a user-centric uh, approach at thinking about security. Um, I'm Dan Finlay from MetaMask. I've been working on it for 5 years to the day as of today, or sorry, 5 years since we launched. I was working on it for a little while before that. And MetaMask is a cryptocurrency wallet that lets you connect to different websites, and those websites are able to suggest interactions to you that could be financial, or they can involve different smart contracts that live on a blockchain. This has forced us to think about security in the highest possible terms, because our users are constantly subject to all kinds of phishing, attack, risk, hacks, you name it. They're trying to do it to our users. So the question of cryptocurrency and the kind of broader aspiration of the decentralized web is, can we organize society better on computers? And I think that the simple answer is only if we can use computers in a remotely sane and safe way. If we build our government on computers and they can all be hacked, well, then our government is only as safe as we are not hackable. So I think this really calls to question our computer security, and why do we accept hackability as such a primary feature in computer systems today? Why is it that ransomware only gets attention when cryptocurrency is involved, and then we shame cryptocurrency for creating incentive in a payment channel instead of looking at, like, what are the root causes that make computer systems so fundamentally hackable and make people so easy to fish into situations where they get hacked? Um, so hopefully through this series, we're going to look at user interfaces. We're going to look at secure systems. We're going to look at attempts to build secure systems by various teams, and we're going to talk about what people look for in a secure system, what people tend to do, what they tend to want to do that tends to get them in trouble, and how we can build our systems to accommodate user intention and user versatility, the demand for versatility from a person's tools, so that we can build tools that are dynamic enough to stay secure even under the demands of a living, breathing human being. So let's begin. Ka-Ping Yi he was, I believe, a PhD student from the University of California, Berkeley. The earliest thing I knew him from was actually he made these really great visualizations of Arrow's theorem, which is a theorem related to how ranked choice voting algorithms work, and the different trade-offs that they have. He made the best visualizations. He really helped me understand the trade-offs of voting algorithms during a time when I thought that ranked choice voting was a bit of a panacea. Um, anyways, Ka-Ping Yi, clearly a really great educator and thinker. And here he's taking on the topic of building secure interfaces. So let's see what he has to say. I'm going to just zoom in a little bit here for your benefit. Abstract. The security of any system that is configured or operated by human beings depends on the information conveyed by the user interface, the decisions of the users, and the interpretations of their actions. This paper establishes some starting points for reasoning about security from a user-centered perspective. It proposes to model systems in terms of actors and actions, and introduces the concept of the subjective actorability state. 10 principles for secure interaction design are identified. Examples of real-world problems illustrate and justify the principles. So I thought this would be this is a good first one because it's not getting too nitty-gritty, but it's establishing a baseline of principles that one person suggests we might aspire to. One moment, please. Introduction. Security problems are often attributed to software errors such as buffer overruns, race conditions, or weak crypto systems. This has focused much attention on the correctness of software implementations. However, correct use of software is just as important as correctness of the software itself. For example, there's nothing inherently incorrect about a program that deletes files. It's only when such a program deletes files against our wishes that we perceive a security violation. It follows that the security properties of any system can only be meaningfully discussed in the context of the system's expected behavior. Garfinkel and Spafford give the definition: a computer is secure if you can depend on it and its software to behave as you expect. Notice that this definition is necessarily dependent on the meaning of you, which usually refers to the user. It is impossible to even describe security without addressing the user perspective. Among the most spectacular of recent security problems are the email attachment viruses. Many of these are good real-life examples of security violations in the absence of software errors. At no point during their propagation does any software behave differently than its programmers would expect. The email client correctly decodes the attachment, and the system correctly executes the virus when the user opens the attachment. Rather, the problem exists because the functionally correct behavior is inconsistent with what the user would want. This paper aims to make two main contributions. First, it presents a model to guide thinking about this type of issue, and second, it gives specific recommendations in the form of 10 interaction design principles for secure systems. Among many designers, there is the pervasive assumption that improving security necessarily degrades usability and vice versa. The decision to favor one or the other is typically seen as a regrettable compromise. For example, commonly suggested security fixes involve having the computer ask for confirmation. Yet we are also warned against annoying the user by asking too frequently. In the end, these judgment calls are often made arbitrarily. A coherent interaction model will help designers resolve these dilemmas. I take the apparently radical position that security and usability are not fundamentally at odds with each other. In fact, it should be clear upon reflection that the opposite makes more sense. A more secure system is more controllable, more reliable, and hence more usable. The more usable system reduces confusion and thus is more likely to be secure. Security advocates and usability advocates both want computers to correctly do what users want. No more, no less. The results presented here come from discussing design challenges and users' experiences at length with designers and users of software intended to be secure. After much debate and several iterations of refinement, we've tried to form a concise set of principles that covers many of the important failure modes. This paper is heavily abridged due to last-minute space restrictions. For a complete version, please visit this site. It is not there. I have asked Copying to provide the full unabridged text. He says heavily abridged. I mean, I desperately want the full paper. I have not yet got my hands on it. I'll have to do a sequel if he ever provides it. To related work. Yeah, and I've tried the Internet Archive. There seems to be relatively few development efforts in computer security that have seriously emphasized user interaction issues. The Adage project, a user-centered authorization service, is probably the largest such effort to date. There have been several important usability studies of security applications, all of which have shown the devastating impact that ignoring usability issues can have on the effectiveness of security measures. To my knowledge, this paper is the first attempt to propose a structured framework for design thinking and to suggest widely applicable guidelines for secure interaction design, as opposed to studying a single application or mechanism. Simultaneously addressing all the principles presented here is admittedly a significant design challenge. Lest they seem too idealistic to be satisfiable, it is worth mentioning that there is an independently developed prototype of a secure desktop shell that largely succeeds in satisfying most of these principles. We'll have to look at that citation number 3 later. Design principles. The following sections present a preliminary set of guidelines for secure interaction design. They're a snapshot of an ongoing process of refinement. Applying them in practice will help to assess their correct completeness. Sufficiency cannot be proved, as it is impossible to guarantee the success of a user interface. So our criterion for admitting something as a basic principle is that it be a necessary and non-trivial concern. I will argue that each principle is necessary by showing how its violation would likely yield a security vulnerability, and show that the principles are non-trivial by pointing out that violations exist in real software. Cool. So you got to have it to be safe, and people don't do it in practice. The principle of least privilege, or sometimes known as the principle of least authority, is a starting point for our reasoning. It is better to think of our design principles in the context of least privileged systems rather than current systems not designed in a least privileged style. A language-based security system, such as Java's sandbox, is one kind of model that one could hope to satisfy these principles. Other platforms designed around the least privileged concept include the E language by Mark Miller, Kikos, and Eros. The design principles are listed here with the detailed explanations to follow. In the statement of these principles, the term actor is used to mean approximately user or program, but this term will be explained more precisely below. The term authority refers to the ability to take a particular action. Path of least resistance. The most natural way to do any task should also be the most secure way. Appropriate boundaries. The interface should expose and the system should enforce distinctions between objects and between actions along boundaries that matter to the user. Explicit authorization. A user's authorities must only be provided to other actors as a result of an explicit user action that is understood to imply granting. Visibility. The interface should allow the user to easily review any active actors and authority relationships that would affect security-relevant decisions. Revocability. The interface should allow the user to easily revoke authorities that the user has granted wherever revocation is possible. Expectability. The interface must not give the user the impression that it is possible to do something that cannot actually be done. Trusted path. The interface must provide an unspoofable and faithful communication channel between the user and any entity trusted to manipulate authorities on the user's behalf. Identifiability. The interface should enforce that distinct objects and distinct actions have unspoofably identifiable and distinguishable representations. Expressiveness. The interface should provide enough expressive power, A, to describe a safe security policy without undue difficulty, and B, to allow users to express security policies in terms that fit their goals. And finally, clarity. The effect of any security relevant action must be clearly apparent to the user before the action is taken. Cool, so there's our little review. I will probably be riffing alongside the text as we go through the individuals. First, we're going to get into some terms. The user and the user agent. Thus far, we've mentioned the user several times, so it's necessary to precisely define what is meant by the user. For the purpose of this discussion, the user is a person at a computer using some interface devices such as a keyboard, mouse, and display. We're concerned with the software system that is intended to serve and protect the interests of the user, which is called the user agent. On a single user system, the user agent is the operating system shell, through which the user interacts with an arena of entities such as files and programs. On a multi-user system, other users use their own user agents to interact in the same arena. When the system is connected to the internet, there's a new level of interaction. Now, the arena of the single computer is nested within the larger arena of the internet. A new kind of user agent, such as a web browser, now represents the user's interest in that larger arena of interacting entities. But in the smaller arena of a single computer, a web browser is merely one of the participants, and the user's interactions with it are mediated by the lower level user agent, the system shell. The browser might be used to contact yet a third user agent, such as a web-based interface to a bank, operating in it yet a third arena of financial transactions among account holders, and so on. This distinction is explained mainly to avoid confusion among levels of user agents. We will not directly address communicating through multiple user agents here. We consider only one level at a time. The rest of this paper discusses the design of any user agent serving a user. The 10 design principles can apply to all kinds of users, not just end users of applications, but also system administrators or programmers. using whatever software they use for their tasks. Different users will have different expectations and needs, so the design of any secure system must begin with a clear understanding of those needs. The principle of least resistance. Number one. This is a bit of an easy one. You might already get where it's going, right? So, in the real world, there's often no relationship between how safe or unsafe actions are and how easy or hard they are. It takes more concentration to use a hammer safely than unsafely, for instance. We all have to learn by being told, by observing others, and often by making painful mistakes which ways of doing things are safe. Sometimes, through the design of our tools, we can make it easier to do things safely. Most food processors have a switch that let them run only when the lid is closed. On power drills, the key for opening the drill chuck is often attached to the power cord so that unplugging the drill is a natural prerequisite to changing the drill bit. In both cases, a bit of cleverness has turned a safety precaution into a natural part of the way work is done, rather than an easily forgotten extra step. Most users do not spend all their time thinking about security. Rather, they're concerned about accomplishing some useful task. It's a human nature to be economical with the use of physical and mental effort and to choose the path of least resistance. This can cause the user to work against security measures, either unintentionally or intentionally. The primary consideration is to keep the user's motivations and the security goals aligned with each other. There are three aspects to this. First, observe that the ultimate path of least resistance is for the user to do nothing. Therefore, the default settings of any software should be secure. This is Salter and Schroeder's principle of fail-safe defaults. It is unreasonable to expect users to read the documentation to learn that they should need to change many settings before they can run software safely. Second, consider how a user might work against security measures unintentionally. User behavior is largely unguided by perceived affordances. It's largely guided by perceived affordances, the visual and non-visual properties of the interface that suggest the available modes of interaction. Affordances, I'm not sure we're going to be reading an article that uses that, but it's something like a button that's associated with your ability to do something. So composing an email, an affordance of an email draft is to save or to send. Um, an affordance of a cryptocurrency token is to send it, to grant an allowance from it, maybe to nickname it. Those are kind of it. An affordance of a domain name is to assign it to an IP address, to assign a subdomain, to assign new name zones or whatever. So there's a little crash course in affordances as it's used in secure UI literature. Second, consider how a user might work against security measures unintentionally. User behavior is largely guided by perceived, I'm repeating. If a button for security function does not look clickable, the user might never notice that it is an available action. So make your security affordances obvious. Third, consider whether users will subvert security intentionally. If operating securely takes too much effort, users may decide to circumvent or ignore security measures while completely aware that they're doing so. There is a security risk in systems where the secure patterns of usage are inconvenient. Each inconvenience increases the probability that the user will decide to operate unsafely. All of these aspects can be summarized by the principle of the path of least resistance. The natural way should be the secure way. An example of somebody bypassing security for convenience would be like you give somebody a link to a document that only they can read, and so they can't share it with somebody, and so they make a copy of it so they can share the copy. And then somebody might give them they're not allowed to share the ability to edit it, so they might ask somebody to edit their copy. Now they pass it to them, and now they have to paste their edits over yours, which makes merging the changes a pain, but that's what you get for making it impossible to delegate. You've introduced an insecurity from the user's inconvenience. All right. All of these aspects, sometimes security goals might seem to oppose the desire to make things easy. However, there are truly in conflict, less These are truly in conflict less often than one might think. Tightening security has to do with having more specific information about the user's intent so it can be achieved safely. Often, this information is already conveyed in the user's actions. It just needs to be applied consistently to improve security. In the few remaining situations where it's absolutely necessary to introduce a new inconvenience for the sake of security, provide a payoff by making productive use of the extra information the user is asked to provide. For example, consider a multi-user system that requires a login procedure. Entering a password is an extra step that is necessary for security but has nothing to do with the user's intended task. However, the login information can be used to personalize the experience by providing a custom desktop, menu of favorite programs, and so on, to offset the added inconvenience. This helps keep users from trying to circumvent the login process or choosing to use a system that doesn't have one. Objects, actors, and actions. To interact with the world around us, we build a mental model of how it works. The model enables us to predict consequences of our actions so we can make useful decisions. Most concepts in the model fall within the two fundamental categories of objects and actions. This division is reflected in the way that nearly all languages, natural or invented, draw the distinction between nouns and verbs. Some objects are inert. Their behavior is simple enough to be completely predicted using physical laws. For instance, if a cup is pushed off a table, we expect it to fall to the ground. In Dennett's terms, our model adopts the physical stance towards a cup. On a computer, one might say a text file is such an object. One can perform actions on the text file, say copy or delete it, with simple consequences, but the file does not appear to take actions of its own. Some objects, however, have their own behaviors. We call these objects actors, since they are capable of taking action. Even though such objects exist in the physical world and still follow physical laws in principle, their behavior is too complex to model using only physics. Since we can't predictably predict exactly what an actor will do, we proceed by estimating reasonable bounds on its behavior. To a computer user, an application program is an actor. There's some expectations about what the program will do and some limits on what it should be able to do. But no user can know exactly what a program instruction is being executed at any given moment. Even though the operation of the program may be completely deterministic, we cannot take a physical stance towards it because it is too complex. Instead, we base our model on an understanding of the purpose for which it was designed. Dennett calls this taking the design stance. Other users are also actors. However, rather than having been designed for a purpose, their behavior is directed by their own motivations and goals. As they're conscious entities, we model their behaviors in terms of their beliefs and intentions. That is, we adopt what Dennett calls the intentional stance. Incomplete knowledge of the design, beliefs, or intentions of an actor produces uncertainty. We limit this uncertainty by applying the physical stance. For example, when one is inside a locked house, one has no need to model the intentions of any people outside the house because one is relying on the physical properties of the house to keep them out of the model. Building models of actors is something we humans are very good at. Bruce and Newman have examined in detail how the comprehension of Hansel and Gretel requires us to model actors models of other actors models, and so on, many layers deep. Yet such complex modeling is a routine skill for small children. There's also evidence. Wait, let me just step through that. So the kids are going for a walk. Okay, so they're thinking about themselves in the future, so they drop some breadcrumbs. Okay, and then we have to think about the birds eating. Okay, but then the witch, she makes a candy because she's modeling kids which themselves pursue candy, and so she's modeling, and then they get there, and I don't know, where's the modeling. Maybe when their dad comes to chop the witch up, he recognizes he's modeling the witch's intention of modeling the children's understanding of her house's appearance, and understands that she's basically fishing them. So I guess that's an example of 3-layer deep modeling, and it's very, very natural and casual for us, right? Cool. That's an interesting point. I hadn't thought of how deep, just how deep, a nested interpretation of others' intentions this children's story is. But yeah, it's a very, very natural human thing, huh? There's also evidence from computer-human interaction research that people perceive computers as social actors, even though machines do not actually possess human motivations. Both these reasons suggest that we indeed form our mental models of computers in terms of actors and actions. It is no coincidence that this is reminiscent of object-oriented programming, since the designers of Smalltalk also sought to match our mental models of the world. Given this foundation, we can now formulate a more precise interpretation of Garfinkel and Spafford's definition of computer security. Our new definition is: a system is secure from a given user's perspective if the set of actions that each actor can do are bounded by what the user believes it can do. Now, I'd say it's an extension of the earlier one. I don't think it's a violation of it, right? Because it's still saying the system's behavior is within the user's expectations, but now we're saying the user is modeling multiple actors within the computer's system. So we're talking about the computer as a multi-entity environment. The system image and the user model. When a designer creates a system, the designer does so with some model in mind, but the designer doesn't get to communicate directly with the user. Rather, the designer decides on how the system will work, the system presents an image to the user, and the user builds a model from interacting with the system. Communication of the model occurs only via this system image. It's a mental image, image in the Platonic sense. Aggregation, the actual working of a computer system, is very complex and involves a great many subcomponents and operations. To make the system comprehensible, the system image aggregates objects and actions into a smaller number of units. Objects may be grouped by related concept or purpose. All the individual bytes of a file are usually taken together, given a single name, and presented as a single manipulatable object. No, he's getting ahead of himself. That's the principle of appropriate boundaries, if I'm not mistaken. He's getting at. Actions may be grouped by concept, by locality and time, or by causality relationships. For example, while a request to open a web page may involve many steps, looking up a host name, opening a connection, sending a request, and so on, it is presented as a single action. Most user interfaces allow the user to control some grouping in order to reduce their own mental effort. For instance, in most desktop operating systems, one can move a collection of files into a directory and then move, copy, or delete the entire directory with a single operation. Users can perform subjective aggregation on the file objects. Systems with end-user programming features, such as macros, allow the subjective aggregation of several actions into a single action. Yep, letting people define their own boundaries. Here it is. That was all set up for number 2. The principle of appropriate boundaries. Aggregation is important because it defines the terms in which authorities can be expressed. The user's model deals with concepts such as actor X can perform action Y on object Z. The boundaries of the objects and actions are found by observing the system image, which conveys these boundaries through the methods it provides for identifying objects, communicating with actors, taking actions, and so on. Here's an example to demonstrate the significance of choosing boundaries. Consider the idea that a secure operating system should let the user control the granting of authorities to programs. If a program spawns multiple processes, must the user separately grant authorities to each process? Or if a program relies on software modules or shared libraries, should the user have to separately control the authorities of every module? No. We resolve the dilemma by declaring that the boundaries between actors in the system image, which are also the boundaries of authority control, should be consistent with distinctions that the user cares about. Any boundary that could have any meaningful security implications to the user should be visible, and those that do not should not be visible. Stated another way, the interface should distinguish between objects and actions along boundaries that matter to the user. If the distinctions are too detailed, there's a greater risk that users will overlap or leave out specifications. However, if the boundaries are too few, users will be forced to give away more authority than they intend. The right distinctions can be discovered by asking, would the user ever want to manipulate this authority independently of another? To grant authority to this actor but not another? to permit access to this resource but not another. Supporting good distinctions sometimes places requirements on the software system behind the user interface. In the case of our example, since it would be infeasible to insist on separate control of authorities for each software component, the system should support the safe aggregation of components into useful conceptual units, that is, applications, such that reasoning about applications as individual actors holds valid. It follows that the system should enforce the corresponding boundaries. Whenever two applications use the same software module, that module should be unable to convey authority between the applications. Ooh, that's getting to the old confused deputy attack. I don't think we'll be getting into that on this reading series, but we'll see. Maybe we'll have an extended version where we get into it. Like how can a software program be confused when it's managing authorities on behalf of multiple other agents? The actor ability state. Among other things, the user model contains some knowledge of actors and their abilities. As a starting point for talking about the user's conceptual state, let us consider a very simple model where the user knows about a finite set of actors, actors 0, 1, 2, etc. They can have an effect on the system where the first actor is the user and there are n other actors. Each actor is associated with an alleged set of potential actions, P for potential. One can think of PI of that actors as the user's answer to the question, what can you do that would affect something that I care about? Or what can that actor do that would affect something I care about? The knowledge of actors and abilities then consists of a set of actors and their potential actions. Since the user believes their own possible actions to be the set of available actions he or she can perform, the user will always choose to do actions from that set. In order for the user to choose actions that are actually possible, PO, sorry, since they said it, it sounded tautological to me, so I just want to see how they're distinguishing. An alleged set. So P, it's not their potential actions, it's their alleged set of potential. So the user believes their alleged set is what they can do. But in order for them to choose actions that are actually possible, then the alleged set should be a subset of their real abilities. Since the user believes that another agent's alleged possible actions is the set of available actions for that other actor, the user expects that any action taken by that actor will be a member of that actor's alleged possible actions. To uphold this expectation, that alleged actor's possible actions must be a superset of that actor's real abilities. The other way, right? You need to have available to you a subset of what you can really do. And to predict other people's actions, you need to perceive a superset of what they can do, because you need to be prepared for more than what is possible. Prepare for the worst, plan for the best, as they say. If we write RI for actor I's set of real abilities, so the real possibilities as opposed to the alleged possibilities, our no surprise condition can be summarized as agent zero's perceived actions must be a subset of the real actions, and any other agent's actions must be a superset of their real actions for anyone other than the user themselves. Yeah, okay, cool. Principle of explicit authorization. It's essential to keep the actor ability state in the user's model accurate at all times, since the user will make security relevant decisions based on this state. To stay synchronized with reality, the user must be in control of changes in the actor ability state. To maintain that another actor's perceived abilities are less than what they can actually do, we require that only explicit user action can cause another action's real abilities to come to exceed our perceived set of their abilities. Explicit authorization is perhaps the most basic requirement for controlling authority in any system, and is a direct descendant of Salter's principle of least privilege. Requiring each authority to be explicitly granted increases the likelihood that actors will operate with the least authority necessary. Without such a restriction, the user becomes responsible for finding a potentially unlimited set of implicitly granted authorities to disable before the system is safe to use. In current systems, applications often have complete access to the network and file system without ever having been explicitly granted those authorities. At first glance, it may seem that this principle is in conflict with the principle of the path of least resistance. Must we constantly intercept the user with annoying security prompts to confirm every action? I mean, I run Little Snitch, so I personally have chosen that for myself. But Copying E says no. Most of the time, the user already provides plenty of information in the course of performing tasks. The system must merely honor the manipulations of authority that are already being communicated. For example, if a user asks an application to open a file and makes a selection in a file browser, it's already clear that they expect the application to read the file. No further confirmation is necessary. The single act of selecting the file should convey both the identity of the chosen file and the authority to read it. In many situations, combining designation with authority yields an effective solution that improves both security and usability. And for those of you playing OCAP bingo, combining designation with authority is straight out of Object Capability Security 101. You know, in the programming language lexicon, the idea that you should be able to combine your syntax with a security policy is a programming language ideal that Copying is here taking to the user interface layer, saying, can't we unify the usability and the security policy into one thing? You know, when you put a key into a door lock, the act of using the key is the act of proving you have the key. Some objects just embody these principles. So we can look out for opportunities to do that ourselves. One can judge when explicit authorization is necessary on the basis of a user expectations. One can judge when explicit authorization is necessary on the basis of user expectations. Okay. For example, if there's a window that clearly belongs to an editor, one can expect the editor to draw in the window. However, it would certainly be unexpected for the editor to spontaneously delete a user's files, just as it normally requires an explicit action for the user to delete files. So, should it require explicit action for another actor to acquire the ability to delete them? The judgment of which authorizations should be explicit should be based on the potential consequences, not on the technical difficulty of the granting decision. Any authority that could result in unexpected behavior should be controlled by the user. If the user cannot readily understand the consequences of granting an authority, then it should never be granted at all, not merely hidden under some advanced section of the interface. If a truly necessary authority seems to require an unusual degree of technical knowledge, then the model presented to the user probably needs to be rethought in simpler terms. Tough love for those who want to delegate crazy authorities. One moment. The principle of visibility. If the actor ability state begins as a known quantity, some safe minimal set of authorities, and we're in control of each change in the state, then in theory, we know enough to ensure our state remains accurate. However, there will be situations where one comes upon a new system in an unknown state. Moreover, it is unreasonable to expect a user to keep a perfect record of all grantings. Human memory is fallible and limited in capacity, so we must enable users to update the actor ability state in their heads at any time. This is not to say that the interface should display all of the low-level authorities of all the components in the system as a debugger would. Though as a programmer, I kind of like that view. Rather, it should show the right information for the user to ascertain the limits of what each actor can do and should do so in terms of actors and actions that fit the user's mental model. Visibility of system state is advocated as essential for usability in general. Likewise, visibility of authorities is necessary for users to understand the security implications of their actions. It makes sense to show the actor ability state in terms of the granting actions that brought it about. Past granting actions having no effect on the current state, such as access given to applications that have terminated, need not be given. It is helpful to identify authorities by inspection of either the holder or the accessible resource. Uh, by inspection of either the holder of the available, right. So you might want to browse your authorities by who did I grant it to, or who did I grant this given authority to. Without visibility of authorities, any application could retain and use a granted authority with undetected and indefinitely, once the user has forgotten about the granting action. Yeah, in MetaMask, this is the current case for our token allowances, but we are planning to add a revocation, the visibility of allowances and the ability to revoke, and you bet principle of revocability is one of these. Speaking of which, I'm going to just take a quick moment to add a couple extra notes. Second pass notes. Sorry, so I just wanted to note that there's an interesting thing there. Yeah, browse authority by recipient or authority. Yeah, I like that. All right. Windows and Unix systems typically run dozens of background processes. It should be emphasized that this principle does not require the interface to display all of these processes. Processes like the kernel swap daemon are not part of a typical user's model and should not be considered actors. Consequently, system behavior should maintain consistency with the model, whereas processes are not actors. The system must strive to maintain the appearance that the swap daemon has no effect on the user's world of files and programs. One of the most widely publicized examples of a harmful background process is the Back Orifice program, released by Cult of the Dead Cow in 1998. Hey, isn't that one that presidential candidate from Texas was part of? Falling flat on the name right now. Anyways, this program is an actor since it can modify files and transmit them over the network without user initiation, and therefore should be visible in the interface. Although Microsoft denied that there was a Windows security issue here. The fact that Windows allows Black Orifice to run invisibly is what makes it so dangerous. Wait, the program is an actor. It allows modifying files and transmitting them over the network without initiation. Wow. Yeah, and Microsoft denied that was a problem, huh? They're like, programs should be allowed to manipulate files. I mean, how else do you make a file sweeper or a backup program, right? I can understand how they were thinking, but I mean, look at this violation of user expectation, right? It's like, you got a problem. Principle of revocability. Hey, didn't I say we'd get to this? To keep the actor ability state manageable, the user must be able to prevent it from growing without limit. Therefore, wherever possible, the interface should allow the user to revoke granted authorities. Another argument for facilitating revocation is the need to accommodate user error. It is inevitable that mistakes will be made. Any well-designed system should help recover from them. In the context of granting authorities, error recovery amounts to revocation. One might intentionally grant an authority to a program and later discover that the program is untrustworthy, or one might inadvertently grant the wrong authority by mistake. In both cases, the granting decision should be reversible. Note that revocation prevents further abuse of an authority, but it is not always possible to undo damage caused by an abuse of an authority while it was available. Now, imagine access to a file. Once you've given information, it's potentially exfiltrated. You can never guarantee it wasn't manipulated or sent or abused in some way. Thus, interfaces should avoid drawing an analogy between revoke and undo. Revoke is better described as desist. Very well. Principle of expected ability. Whereas the preceding three principles deal with managing other actors' abilities, the perception of the user's own abilities can also have security consequences. Users sometimes make decisions based on the expectation of future abilities. There can be serious security consequences if the user expectations are wrong. The false expectation of an ability might give the user a false sense of security or cause the user to make a commitment that cannot be fulfilled. Explicit authorization addresses one half of the no surprise condition. This principle addresses the other half, that a user's perceived abilities are the subset of their real abilities. For example, consider a system where granted authorities are usually revocable. If the user encounters an authority that cannot be revoked, the interface should make this clear, as it could affect a user's granting decisions. I think this is one that I have not deeply internalized, and it's pretty short, so it kind of makes sense. There's a small addendum to it. Input and output. Observation and control is conveyed through input and output. So the ability to use the system securely relies on the integrity of the input and output channels. Perception of your own abilities based on future abilities. Right. Yeah, okay. So, users sometimes make decisions based on the expectation of future abilities. The false expectation of an ability might give the user a false sense of security. So basically, if you're ever going to take an action that might limit your future actions, you should make extra clear that that's going to happen. I thought of an example. In Ethereum, on our Ethereum blockchain, you need a little bit of ether as the network fuel to perform any other transaction with normal externally owned accounts. When a user is sending away their last ether, if they have other assets in that account, it will prevent them from doing anything else until they replenish their ether. And that includes with if they're performing a swap and they're trying to, trade all their ether for something else. Well, some of that ether was what gives you the option to do some other things. So there's this kind of like math that we end up needing to do, which is like, how much ether do you potentially need to do all the things you might want to do with what you have? What should we assume you're going to want to, you should at least have enough ether in an account to send away all of its assets, let's say. But even that ether cost varies, the transaction costs vary over time. So actually estimating it, good luck. At the very least, we can warn you if you're going to completely drain the account. So I'm going to just take note of that. Cool. Principle of trusted path. This is a cool one. The most important input and output channels are those used to manipulate authorities. If these channels can be spoofed or corrupted, the system has a security vulnerability. Hence, the principle of the trusted path. The user must have an unspoofable and incorruptible channel to any entity trusted to manipulate authorities on the user's behalf. The authority manipulating entity could be a number of different things, depending on the domain. In an operating system, the user needs a trusted path to the interface components for handling permissions and authentication. Windows, for example, provides a trusted path to its login window by requiring a user to press Control-Alt-Delete. These keys cause a non-maskable intercept that can only be intercepted by the system, thus guaranteeing that the login window cannot be spoofed by any application. In a language system for running untrusted code such as Java, this issue also needs to be addressed. In MetaMask, we're a browser extension, and browser extensions have the option of adding a little toolbar icon. And so when a user clicks that toolbar icon, there is an unspoofable action view that we're able to render trusted information in. However, that doesn't prevent websites from providing their own kind of impersonation of that pop-up. What most or many users don't know is that actually there's no way for a website to open a web extension's action view. It can only be initiated by user interaction. But meanwhile, a website, also, if you see a pop-up from a web extension, if there's no URL bar, that can only be from a web extension, but that's not really well known, so it doesn't preserve much security. If it's from a website, though, it will always have a URL bar. So if you ever see a pop-up and it has a URL bar, you can look at the URL to understand the origin that's presenting that pop-up. Also, these days, browsers have pretty good pop-up blockers, so it's not as big of an issue. I don't know if you can hear the ice cream man near me, but no, I'm going to resist. I'll treat myself to something dinner right after this. All right. I don't know if you can hear that, but it's mildly distracting to me. I'll just briefly pause recording. All right. Principle of identifiability. The ability to identify objects and actions is the first step in proper communication of intent. When identity is threatened, either by inadvertent collision or by intentional masquerading, the user is vulnerable to error. Identification has two aspects: continuity, the same things should appear the same, and discriminability, different things should appear different. That something is perceived to have an identity depends on it having some consistency over time. When we see an object that looks the same as something we saw recently, we're inclined to believe it is the same object. If an untrusted program can cause an object to look the same as something else, or it can change the appearance of an object in an unexpected way, it can produce confusion that has security consequences. The same is true for actions, in whatever way they're represented. Actions are just as important to identify and distinguish as objects. I have a little caveat there. For example, if you have a trusted path to your secure actions, like let's say your wallet, somebody else can present you a pop-up that impersonates your wallet, and they can show you a send button, but clicking send tokens on that wallet at most can make you think you sent money that you didn't send, but it can't make you send money that you did send. So there is actually a little bit, is a kind of nuanced point, but there is meanwhile an ability to, if they successfully spoof you, trick you into believing something that you shouldn't believe. So the point is still valid. Being able to represent is dangerous as a same object. Even for actions, but actions I swear are a little bit less sensitive. The real danger we see when web pages are spoofing our interface is usually like a website says, "Hey, we're MetaMask. We forgot your secret recovery phrase. Would you please paste it here?" And then users paste it. In that case, the action wasn't actually provided by the interface. It was actually requested by the interface, and it was an action that the user had at their available to them by virtue of the nature of a private key cryptography. We're working at providing users more options than just holding simple private keys, since those are so easy to misuse. But it's a good example of there was no sensitive action provided by that phishing attempt. The phishing wasn't able to provide an imposter action that was dangerous. It was only able to provide like a path of that, a course of action that was deceptive. Anyways, I'm just trying to work through this myself. Meanwhile, so can a program make an object look the same as something else? Here's a good question. What about websites where the domain is similar, right? This happens all the time on like a search engine phishing. If you search for any cryptocurrency wallet support on Google, there's a decent probability that the top ad recommended by Google is going to be a phishing attempt. There's going to be some criminal organization that paid for that ad, and they're going to have some URL that's very similar to your target site with maybe a letter different or something. So you might ask, are domain names safe? I mean, if our ability to recognize a name is, so easy to mistake, like just an L versus a capital I here or there is enough to spoof a valid name, then why do we put so much weight in domain names? I think the typability is the great value of a domain, but if we use them for identifying the source of information, we can find ourselves into a tricky situation. And I believe in the second or third episode of this, we'll be getting a little bit deeper into the security of name systems. All right. Note that it is not enough for representations of distinct objects and actions to merely be different. They must be perceived by the user to be different. Even a choice of typeface can have security consequences. It's not enough for two distinct identifiers to be different strings. Oh, look, he's going to make the point that I made. They must be displayed with visually distinct representations. In some fonts, lowercase l and the digit 1 are very difficult to distinguish. With Unicode, the issue is further complicated by characters that combine to form a single accented letter, which can cause different character sequences to be rendered identically on the screen. It's not safe to assume that all actors will choose unique and consistent representations, so the continuity and discriminability of the objects and actions are things that must be enforced by the system. This is the principle of identifiability. I think I'm just actually making a different point than him, though, because he's saying like, oh, well, make sure your fonts distinguish between these digits. And I'm saying even if the fonts distinguish between those digits, like people are reckless and sloppy, and they don't read things really closely. And so if your security model relies on a close read, if your security model allows strangers to represent their own name with the same gravitas or the top search result as a valid one, um, then it doesn't really matter what damn typeface you're using, right? There's something a little bit more fundamentally wrong here. Um, Again, stay tuned for the pet names episode. We're gonna have some fun. Um, Next, principle of expressiveness. Sometimes the security policy may be specified explicitly, as in a panel of settings. Other times it's implied by actions in the normal course of performing a task. In both cases, there's a language of settings or actions through which the user expresses a security policy to the system. If the language used to express policies does not match the user's model of the system, then it's hard to set policy in a way that corresponds with intentions. In order for the security policy enforced by the system to be useful, we must be able to express a safe policy, and we must be able to express the policy we want. For a good example of an expressiveness problem in real life, consider the Unix file system. Oh no, I prefer not to. Since each file can only be assigned to one group, it's impossible to share a file only for reading by one colleague and writing by another. Because the commands for setting permissions lack sufficient flexibility to express some kinds of sharing, users are sometimes forced to share files unsafely with everyone. The principle of clarity. When the user is given control to manipulate authorities, we must ensure that the results reflect the user's intent. We rely on correct software to enforce limits on each actor, but correctness of the implementation is irrelevant if the policy being enforced is not what the user intended. This can occur if the interface gives misleading, ambiguous, or incomplete information. The interface must be clear, not only about granting or revoking authorities. The consequences of any security relevant decision, such as a decision to reveal sensitive information, should be clear. All the information needed to make a good decision should be accurate and available before the action is taken. An interface can be misleading or ambiguous in nonverbal ways. Many graphical interfaces use common widgets and metaphors, conditioning users to expect certain unspoken conventions. For example, round radio buttons signify an exclusive selection of one option from many, while square checkboxes signify individual yes-no decisions. An ellipsis at the end of a menu command indicates that additional options must be specified before an action takes place, whereas the absence of an ellipsis implies that an action will occur immediately. Visual interfaces often rely heavily on association between graphical elements, such as the placement of a label next to a checkbox, or the grouping of items in a list. Within a dialog box of security settings, we might rely on the user to correctly associate the text describing an authority with the button that controls it. Clarity can be evaluated in terms of the Gestalt principles of perceptual grouping, which suggest that visual associations are guided by proximity, closure, symmetry, figure-rounded separation, continuation, and similarity. Okay, I'm gonna have to look that up because that just sounds like it's begging to be read in the future. All right. Summary. In order to be able to use a system safely in a world of unreliable and adversarial software, a user must have confidence in all of the following statements. Things don't become unsafe all by themselves. Explicit authorization. Actually, I'm going to do a little test here. For each one, I'm going to see if his two claims hold true, that they're non-trivial and what's the significant? It's like if it was absent, you could be insecure, and things have made those mistakes. So things don't become unsafe all by themselves. I'd say that Microsoft made it very clear that it can be unsafe to leave a program running all by itself. So that's non-trivial, um, and if you don't do it, then yeah, then bugs happen. Okay, I'll give that one a pass. I can know when things are safe, visibility. So if I can't have visibility into the state of a system, can I become unsafe unpredictably? Um, I would say yes. Let's say if I'm gonna draw from crypto. That's probably my cheap move. But if you put tokens into a smart contract, it could be getting drained when you're not even watching it. I don't know if you want to count that as part of your trusted compute base. Um, And do people do that in practice? You bet. Revocability, yeah. Shame on me. We've taken years to get revocability into MetaMask, at least for token allowances. So it definitely happens in practice. And does it hurt people? Well, there are definitely things that people grant allowances to that they shouldn't. Whether or not revoking it would be done in time would be an exercise to the user, but I think we can only say we ought to be able to try, especially since some contract vulnerabilities are discovered later. So if people were good at revoking things, they would definitely be safer in some cases. I don't choose to make things unsafe. The path of least resistance. So is it a so yeah, if it's casual and easy and clicking OK many times makes you less safe, yes, obviously that would be an unsafe thing. Is that something that is that a non-trivial, as in software does this all the time or ever in practice? Probably. Uh, I mean, the fact that people are getting hacked all the time, they're getting phished, it definitely implies that people are extending uh, authorities they don't mean to. Um, I don't know if that's an explicit authorization issue or a path of least resistance. Are computers passively unsafe? That's a bigger question to ask. Probably. Can you think of examples? Yeah, this is a video. There's viewers. Hey, can you think of examples of computer software that's unsafe by default? Leave it in the comments below. All right, there you go. I'm doing the YouTuber thing now. All right, and then I can distinguish the things that matter to me, appropriate boundaries. Oh yeah, this is a really cool one. I like it because it's like a principle for deciding what boundaries to have. So for example, yeah, his file concept is perfect. Are there examples of permissions that are too fine grained you don't bother reading them? Well, when's the last time you read through your browser permissions or something? So it's probably fair. It's hard for me to say that things aren't getting inappropriate boundaries. I can't think of good examples offhand, but I'm sure they exist. And of course, if they didn't exist, just like he said, it results in either uh, probably confirmation fatigue from doing too many things you don't care about, or extending authority by granting large boundaries. I think this is an easy one to just take at face value. Um, I can tell the system what I want. Expressiveness. Are there systems that in practice you can't tell it to do what you want? Oh, you bet. Oh my God. I wish I could just shut my phone up on a regular schedule. Like, I know iOS is finally going to do it where you can like turn off notifications for work apps during some hours, for example. But, this is a long road. All software is long going to be trying to express all of users' needs until we're just talking to it and programming it with our voices. I think it's non-trivial. It's obviously non-trivial to get a computer to do what you want, and are and then if they don't do what you want, are we definitely insecure? That's maybe a harder thing to claim. Probably if the thing that you want is a security related thing, um, like privacy, being more specific about sharing your location, um, being more specific about the allowance. Maybe it's you wanted a time constraint as well as an amount restraint on an allowance. There's lots of ways that permissions could be more expressive that I think is obviously beneficial. Um, and then I know what I'm telling the system to do. Clarity. Are there times you don't know what you're doing? Oh my God, have you tried to install software on Mac OS lately? It's like, hey, this software is from an untrusted developer. Do you want to install it? We're like, uh, I guess. Like, do I care that or unidentified developer? Do I care that it's not identified? What they mean is it'll be able to do anything or nearly anything. And they've been changing the rule, right? Like now it seems that they can't access the whole file system by default, and that's very good. But like, does your mental model match what your computer operating system is doing? Like, I think it's very easy to say no. In fact, I'm pretty sure Tim Cook just testified in front of court during the Epic versus Apple case, and he testified Mac OS is a vulnerability-ridden ecosystem, basically trying to argue that iOS and that kind of closed ecosystem, that walled garden approach, is the only way to keep a computer system safe. Is that the truth? Uh, I sure don't believe so, and I sure hope it's not, because walled garden would imply that we're going to be eternally beholden to techno barons or something. But so yeah, I think it's fair to say, yeah. So do I know what I'm telling the system to do? Yeah, obviously we often don't know, so it's non-trivial. Is it critical that you know what you're telling the system to do? I'd say obviously yes, because otherwise it could be doing something you don't want it to do. It's I'll just take an easy way out because this has been a long video already. Lastly, the system protects me from being fooled. Identifiability, trusted path. Um, you bet that's important. If something could impersonate your system, then what are you even typing your password into, you know? Um, and do things violate this? I think things are doing better at not violating this, but honestly, I mean, once you start becoming aware of these patterns, you, like me, might start regularly questioning when you're typing into a box. How do I know that I selected my browser? You know, like, did you alt tab it? Did you click another window? How do you know that other window you clicked wasn't inside another window that was spoofing that window? You know, just little things like that. You know, apps can go full screen. Like, how do you know it's not impersonating your whole desktop? Um, so there's only so much a system can do, and I don't think that systems make a first class effort to like ensure that you always know. But they're doing pretty good. I don't think they're just like totally losing at this. Um, but you know, it's a struggle still. You know, for example, on iOS, I know when you're typing your password on an iOS prompt, I'm pretty sure you get a blue toolbar, right, when it's a system prompt. Or is it? Right? The fact that that's like trivia and not an obviously apparent user interface element kind of tells you that uh, there's a vector for being fooled. Like every time your iOS is, or your, you know, your phone operating system is asking you for a password, you should really, you know, kind of scrutinize that. Look twice. Say, who's asking for my password? Who am I giving my password to? Is this my system? And how do I know it's my system? You know, I think the more you look out for this stuff, and the more you start to realize that modern computer systems are lacking what is probably really obvious improvements in a lot of cases. And more people should probably be thinking like this, especially more people in major companies that are designing the computer systems that we're all kind of forced to use by monopoly. All right, off my soapbox. Conclusion. I've argued that consideration of human factors is essential for security, and that security and usability do not have to be in conflict. In an attempt to provide some foundations for talking about secure interaction design, I've presented the actorability model and a set of design principles. The model is supported by evidence from other research. The principles are supported by direct reasoning, by the model, and by examples of problems in real software. The principles are applied in case studies of interaction problems with proposed solutions available at zesty.ca/SID. I hope this paper will provoke discussion about a user-centered approach to computer security and lead to computer systems that are safer and more reliable, not only in theory, but also in practice. This paper builds directly on previous work with Miriam Walker. Many of the insights in this paper come from Norm Hardy, Mark S. Miller, Chip Morningstar, Craigen Siddiker, Mark Stiegler, and Dean Tribble, who participated in the extensive discussions during which the design principles were developed. Thanks also to Morgan Ames, Verna Arts, Nikita Borisov, Jeff Dunmel, Tal Garfinkel, Marty Hurst, Nadia Henninger, uh, Joanne Hibschman, Josh Levenberg, Lisa Megna, David Wagner, and David Waters for helping and reviewing this paper. And there you go, just for the screenshot ability. Here are the citations. Oh, what was that, number 3? Convex. Oh, Ian Kafdesk. Oh, of course, of course. I've been meaning to get to that one. Okay. Cool. Well, I hope that you've enjoyed this reading of user interaction for design for secure systems by Copying Yi. I know that I've enjoyed this one every time I go through it. Hopefully it's resulted in some interesting thoughts and conversation, um, and yeah, I may do another one of these in the future. Um, but yeah, let me know. Have you used any major operating systems that have obvious violations of these principles? Drop them in the comments. Call them out. Name and shame. How are we ever going to get secure systems if we don't elevate this conversation and make sure that we're identifying these issues and addressing them head on? and let's build secure platforms worthy of broader social coordination together. Thanks a lot for your time. And end. Take care.